Hello and welcome back to Calculus 2, section 8.9 on improper integrals. Oh, there's a cheer in the back. This is awesome. So it's going to be a good class, right? First of all, improper integrals, guys. This is one of those life-turning sections. So from tonight on, your instructors stop being careful and you begin being careful at all times. Because improper integrals would be the ones that are integrals that calculate area under the curve, and what happens is area could be infinite in some cases, right? So if you take a look at problems you had so far, let's say you have a function y equals x, and you are on the interval 0 to 3, you can find area under the curve by simply integrating 0 to 3 x dx to get your x squared over 2 from 0 to 3 and get your 4.5 and move on with your life, right? So that was so far. And any definite integral you ever had, you just used the fundamental theorem of calculus part 1, which stated that the definite integral a to b of f of x dx was any antiderivative f of x computed from a to b, and you just compute f of b minus f of a. And we were very careful with what we give you, because in some cases this can go really wrong. And when this stuff goes wrong in your engineering design, your designs actually explode. And that's the fact. If your integral represents area under the curve integral, right, represents energy, what is the infinite energy? Right? So anytime you accumulate infinite energy, or try to accumulate infinite energy in a small interval of time, well, that's actually what the explosion is. So you know that there are exploding batteries in different, right, devices that came out through the years. Samsung had one, Sony had one, Dell had one, right, and so on, or multiple. So you understand that, and even, you know, if these things are not designed properly, you have to, when you are designing these things at the high level, right, you are actually using integration, because you are making sure that the energy is bounded. You want the bounded energy to be at whatever your battery is going to hold. And if your battery is trying to store the infinite energy and physically it cannot, obviously it has to explode. So many other designs as well. So why do you have to be careful? Well, as I said, so far we were careful to give you something that you can deal with the knowledge that you have up to today. But now you can run into different integrals that look nice, and you know immediately how to integrate. But in disguise, they tend to be living nightmare. What's wrong there?
X can't be, oh
No, you say it.
no.
Yeah.
Because it's ln absolute value of x minus 3, so x can't be, like, the result can be negative. I just don't see why x absolute value can't be.
That's great. What else? That's perfect.
Wouldn't it be absolute value of x?
It would be absolute value of x, yes. So when you put absolute value, it turns everything into positives, sure. What happens when x is equal to 3 in this case? Now, I practiced this. I don't know if I'm going to do a good job, but I did practice. There we go. I tried. So it looks like a tree, but it's not a tree. It's not a tree. This is the nuclear mushroom cloud explosion. Yes. Yes, this is the nuclear explosion, right? That's what happens. I don't know how well I did. So it's okay. All right, good.
I mean, what if that's what you want?
Then in that case, it's okay. Because, no, I'm serious. There is a professor at NGIT who used to work at Los Alamos as a scientist and researcher. And yes, in that case, you are looking for the situations in which you are making the infinite energy, right, go off, right? It's like that. But in our case here, if you're designing a car, you kind of don't want it. You know what I mean? Anyway. So yeah, as much as this picture is not that great, we all understand that x equals 3 is going to lead to that, because you are going to have division by 0, and that's never okay. So now you understand where the dangers hide. So let's talk about improper integrals. And from this point on, no matter which course you're sitting in, Calc 2, Calc 3, differential equations, all of your engineering courses, including physics, anytime you see a definite integral, this is the first thing you have to check. Is it improper? Because if it is improper, you have to use the improper integral procedure, which we are learning tonight. If it's not improper, then whatever calculus you learned before deals with it. Improper integrals are going to have two types. Type 1, easy. Type 1 is going to have an integral that will have infinities in limits. Easy to see, easy to spot. In application, you can say, okay, we have a bell-shaped curve. That area is leaking on both sides, right, going to negative, positive, infinity. So type 1, you will have either one of the infinities or both infinities in the limits. Never an issue with the type 1. Hell breaks loose quickly with the type 2. Because type 2 is the one that goes a to b, f of x dx. It looks just like any other, but a to b holds the vertical asymptote, and that's what I'm writing in blood now over here. AB interval contains vertical asymptote, and that one is the scary one, because if you are not careful, you are going to miss it, and if you miss it, and that's not good. So now, can Calculus 1 solve this problem? The answer is yes, but it's going to get a garbage answer, because if you solve this as ln x minus 3 with absolute values, you plug in 6, you plug in 0, you are going to get some numbers that will tell you, yep, everything is good, where in fact, that one actually is equal to infinity, right? So you're expecting a convergent, you're expecting a finite answer. Let's not use the word convergent yet. You are expecting a finite answer there, and then you try this in practice, and it's just like, what just happened, right? And that's the type 2. So type 1 are easy to spot. Type 2 are the evil ones. And this is why I say that, from this point on, anytime you see the limits given in the integral from tonight's lecture on, you have to check for improper first. Now let's talk about type 1, because that's where we begin. Say you want to calculate integral 3 to infinity for e to the negative x dx. What are you computing here? Well, you are computing simply area under the curve. Curve is e to the negative x. You can graph that because you know, right? So it will be this one. It's the decay curve. And you are going to go to value 3. And then you are going to take the area all the way to infinity. Area is leaking here. So it seems that this should be infinity, right? Because that line will never cross x-axis. It will forever go to the right, which means that it will never close the gap. So it kind of seems, but then we don't know until we solve the problem. Now, how do you solve this problem? Because you can't really plug infinity. Well, we use a hack. And the hack is to change infinity to a finite number, b, because it's the upper limit, and then send that b to infinity, so in the limit. So what I'm going to do is I'm going to say limit b goes to infinity, integral 3 to b. So you see how it's a hack. Like when they say you are not allowed to sell bottled water. That's okay. We're just going to sell a toothpick for $1, and then we're just going to give a complimentary bottle with the toothpick, right? So that's pretty much the same thing, right? You're not allowed to plug in infinity. Awesome. I'll plug in b, and then I'll send b to infinity, right, later. So now what you have here is a standard Calc1 integral. Nothing to worry about, right? You will integrate, you will plug in the limits, you will get some answers, and when you get the answer in terms of b, then you shoot that b to infinity. So let's do that. We have to copy limit in every step until we get to use it in the last step. So like if you have 7 steps before the answer, and you don't write limit 7 times, it's just -7, so it's terrible. And the problem was like 6 points, so it's just like negative whole step. Anyway, what's the integral of e to the negative x? Negative e to the negative x. Beautiful. Computed from 3 to b, and then we go and we say limit b goes to infinity, and we have negative e to the negative b plus e to the negative 3. And now, what happens when I plug in infinity? What's e to the negative infinity?
0.
Very good. We need to, here, let's do it in blue on the side. Limit of e to the negative x as x goes to infinity. Since I have, well, let's do positive x and then negative infinity. How about that? So negative infinity. If I draw e to the x looks like this, but you are going to negative infinity. Negative infinity is this way, so answer is 0, which is why this will go to 0. And the answer is 1 over e cubed. Now we say converges to 1 over e cubed. You can come up with decimals, right? In general, we don't spell the converges, we just say converges to 1 over e cubed. So this was a finite area, even though it was leaking to infinity over here, as you can see, right? So we have to compute you will replace the limit with a finite value, a or b, depending which one you are replacing, and then you will send the limit of that parameter to either positive or negative infinity, whatever you had. Solve the integral regular way, and then at the end, do the limit, because you will have those a and b's inside to solve the limit. Let's try our problem. Let's try another problem. So say you have integral 3 to infinity for 1 over x dx. Doesn't that look pretty much the same as the e to the negative x? Would you agree? That looks pretty much the same, right? As the previous one. You know the steps already. Replace that infinity with limit of b goes to infinity. Replace infinity with the b and do calculation.
Well, they learned that's I don't know. The jar. The jar. Forget effect. Yeah, see? There you go. I have. Wait, he was mentioning
Oh my god! I'm just getting slaughtered right now, it's fine.
something.
Until the D. I'm in trouble. Bullies. You don't have to
They have no sound of death.
Did it explode yet? Yeah, right? All right, let's take a look. So, step number 1, limit as b goes to infinity, because we are replacing the upper limit again. So, limit b goes to infinity, 3 to b of 1 over x dx, which gives us the limit b goes to infinity, 1 over x, what's the ln absolute x, thank you, from 3 to b. So now limit b goes to infinity, we have ln of b minus ln of 3. And now you have ln that goes to infinity. If you take a look at the ln graph, that's ln x. What happens as x goes to infinity? You see that it climbs up to infinity, right? Limit is the y value of the x that you are looking at. So limit is the y value. So the y value for the ln x graph is going up to positive infinity. So this over here would be infinity minus 3. Minus ln 3. Well, and we say diverges. The graph looks very similar to the previous problem. The graph looked very similar to the previous problem. I even started at 3 and went to infinity, right? And now this one diverged. Now, is this the point where you start memorizing? Well, let's see. how about you redo this problem, just put 1 over x squared. So 3 to infinity, 1 over x squared. Let's go. 3 to infinity, 1 over x squared. So integral 3 to infinity of 1 over x squared dx. What the graph for this one looks like? Yeah, similar to the old other ones, right? Looks like that. You go at 3, and you have the pretty much the same deal.
Write it down.
That's what I was gonna do, if I would do negative 2, negative 2 right now. And then you do,
I like this.
yeah, yeah. That is what I do. I don't know if that's correct. That's fair.
Also, people like get your business.
Yeah, so then the negative 1 over x. Kind of thing. Look at There's gotta be stuff here when you say you're like,
Take your time.
I'll get back to you.
What do we have? Another explosion or no?
No
explosion.
No! No explosion now. You go, huh? They all look pretty much the same on the graph. Some of these explode, some don't. Which is why you have to do the entire calculation every time. This is for the first time. And I will say this many times in the next couple of chapters, chapter 10 primarily. You have to retire your common sense, okay? Do yourself a favor, retire your common sense for this section, okay? And just do the calculation so you don't run into any problems, okay? So what do we have? Again, limit, same calculation, limit b goes to infinity, and then 3 to b of x to the negative 2 dx. The integral is, well, first limit b goes to infinity. The integral of x to the negative 2 is x to the negative 1 divided by negative 1, so negative 1 over x, computed from 3 to b. And this becomes limit b goes to infinity, negative 1 over b plus 1/3. When you divide 1 by infinity, you get 0, because you take an object and you cut that object infinitely many times. It's gone. So this goes to 0, and the answer is 1/3, and we say converges to 1/3. So now we have seen 3 problems all of the graph looked very similar, but then some of them diverge, some of them converge to a finite area, which is why I'm asking you to retire your common sense, and the common sense here is if it goes to infinity, it will diverge, because so far, out of 3 examples, I gave you 2 examples that converged and 1 that diverged. It is good time now to mention that this particular section is not teaching you a new integration technique. It's teaching you a hack to deal with the infinity. What types of integrals can you expect? And the answer is all of them. Basic, U sub, trig sub, biparts, partial fraction decomposition, hopefully never, but yes. So all of the methods of integration can be in here, because you are not learning to integrate today. You are learning the hack. You are learning this. That's it. That's what you're learning. The rest of integration is look up your previous sections. So anything can be in here. And clearly these first few examples, right, they were all basic integrals. We can spice up things quickly. What would be a very good example to take a look at? Well, obviously, integral from negative infinity to positive infinity of cosecant, hold on, because this is going to be cosecant hyperbolic squared x dx. Okay. Now this is obviously one of the basic integrals, so it should take. But what is the issue now, guys? Do we all? Yes, we have 2 infinities. Can I write the limit with both of them? No. So what we have to do is we have to break our domain into parts, and then have negative infinity to certain value that you pick, that it's convenient, and then from that value to positive infinity. So that way, you are not going to run into issues. Now, what is the cosecant squared graph? What does it look like? We did that stuff, and I did show the graphs back in 7.3, I believe. Doesn't go to infinity, but it's something like what you're mentioning now. Let's draw. Do what?
Didn't you just say it wasn't a big split?
I did. Just trying to figure out what happened.
Squared.
Oh. Yeah, I gave them. Secant hyperbolic, not. Secant hyperbolic, not cosecant hyperbolic. There we go, much better. Secant hyperbolic squared x. That's what I meant. So when we have a secant hyperbolic, the graph is there we go. Much better. What does this look like? A bell-shaped curve. So if you studied statistics, you know that under the bell-shaped curve, area is equal to 1, and that gives you the probability. So if you say that the average IQ is 100, and then every 15 is a standard deviation, right? And you can take your IQ test and see where you fall on that list. Say you test into, let's say, 118 or whatever. Then you can use a z-score to see the standard deviation, blah, blah, blah. But you can use the z-score to convert into area. Well, those of you who took stats, you know that you had to shovel through those charts with values, right? Why? Because the statistics you took was not calculus-based statistics. That's why you have those charts. Because if you took the calculus-based statistics, you would have the integral to solve that would go from negative infinity to, oh, there they are. Look at that. So now, you get to replace those papers with the improper integral, in this case, that would go from negative infinity to whatever the z-score over here is, let's say 1.1, I don't care, right? So you would actually do the integral, and that would work out to be a decimal number, which is the decimal number you have in that chart. All right, great. So this is just an application. This is just a side, so I'll just put that there in a box. I need to solve this integral. And the way I need to solve this, I have two infinities, is I'm going to break it from negative infinity to 0 plus integral 0 to positive infinity. Because I cannot put two limits, one for limit of a and one limit of b, in the same thing. So I have to have limit a goes to negative infinity, integral a to 0 of secant hyperbolic squared x dx, plus another limit b goes to positive infinity, integral 0 to b secant hyperbolic squared x dx. So I had to break the integral into two over here at 0. You can break it at any point. 0 is convenient. We'll see that 0 is convenient. If you like the pain, you can break it at 1 over e squared. Whatever, right? Don't, but you can. You can break into any number, right? Any number can be used as the breakpoint as you go. So now we have, what's the integral of secant hyperbolic squared? Very good. So it's just tangent hyperbolic x from a to 0 plus, the cool thing is if you break this apart, the other one is the same. So tangent hyperbolic x from 0 to b So now, what I have here is limit as a goes to negative infinity of tangent hyperbolic of 0 minus tangent hyperbolic of a, tangent hyperbolic of a, plus limit b goes to infinity of tangent hyperbolic of b minus tangent hyperbolic of 0. So now, if you look at your tangent hyperbolic graph, which I am trying to get to, well, actually, I can just do the Desmos thing because I have it. Tangent hyperbolic of x. There we go. If you look at your tangent hyperbolic x, it's immediately obvious what? That tangent of hyperbolic of 0 is 0, and we have another one over here. And what's my tangent hyperbolic of a as a goes to negative infinity? I get negative, negative 1, right? I have negative, negative 1, and then the other one will be positive 1, so plus 1, and the whole thing is 2, converges to 2. So tangent hyperbolic of 0 goes to 0. We saw that the tangent hyperbolic cuts through 0, and it's bounded at 1 and negative 1. So as you shoot to negative infinity, the negative infinity will give you a negative 1. You have this negative, and then you have negative 1 for this, so negative, negative 1, plus tangent hyperbolic of b is the other side, and that goes, when you go to positive infinity, it goes to positive 1, and then 1 plus 1 is 2. So this one converges to 2. Now we don't like that for probability, so we scale that down, right? So divide by you put a coefficient in front of the integral of 1/2 and so on. So there are ways to deal with these normal distributions, right, to fit these graphs. You need to also use the scaling of standard deviation sigma and so on. So if you take calculus-based statistics, you will have fun with improper integrals because that's where this stuff comes from. So what I will, yes?
Sorry, so you said you got -1 from graph A.
I got negative 1? Yeah. Because when my x goes to negative infinity, the y value, which is the answer for the limit, goes to negative 1. We can also see that much better on a Desmos graph, which is there. So as x goes to negative infinity, the value for y is negative 1. When x goes to positive infinity for tangent hyperbolic, it goes to positive 1. So, okay, let's sum up type 1 so we can move to type 2, which you are all so patiently waiting for. Type 1 integrals are the ones where infinities are clearly visible in the limits, so you are not going to miss those ever, because you can see it. You immediately unleash the procedure of replacing infinity with a finite value. If it's a lower limit, you will replace it with a. If it's the upper limit, you will replace it with b. So you will immediately do that. And then you will just solve the integral like nothing happened. You will drag the limit with you every step until you get to use it up in the last step of the problem. And your answer will either be a finite value, which we say converges to that, which represents the area under the curve, even though it's leaking to infinity. Or you will get infinity as the answer, in which case we say diverges. And those are the situations that you do not want in your design unless you're designing bombs, as you mentioned before. Third example had also this one. And now we had an example that was leaking area on both sides. And my graph over here actually had extra examples and stuff, so I'm just, whatever. So area leaks on both ends. And when we did the calculation, we said, well, the area converges to 2. So we know that it's finite. So that's the easy part. Now comes the hard part, because these are not obvious unless you are careful to see them. Type 2. Type 2 improper integrals are the ones that have a vertical asymptote in the vertical asymptote in the domain. And that is an issue, because vertical asymptote in the domain, it allows area to leak upwards and downwards, and that could create issues. So the problem that I introduced the concept with was integral 0 to 6 of dx over x minus 3. So this was the problem that I introduced, and I was very happy that you guys picked up that something is wrong, right? Because we would like to solve this and be done, but we see that x minus 3 has an asymptote at 3, which is between 0 and 6. So if I am to graph this, and this is why it's important to have these graphs in your head, right? No one is asking you to learn graphing to torture you, but to actually be able to spot when these situations come up, so you can actually, do your design properly. So this is your 1 over x minus 3 has the vertical asymptote at 3. And if I want to find area under the curve from 0 to 6, then I'm looking at this area here. And it's clear that this area has a problem at the asymptote, because it is going to leak this way and it's going to leak that way. Now, what we learned from type 1 is that not all of these when the area leaks are infinite. Some of them are finite, some of them are infinite. It will depend on the calculation to show what's going on. Now, this is the one of those problems where you have also to break it into 2, because you are approaching 3 from 2 different sides. You see that you have 2 separate leaks. That means that you will have 2 separate limits to deal with them, because it's not the same leak. It's 2 different leaks, right? So because I have 2 separate leaks that I see on the graph, I am going to break this integral into 0 to 3 plus 3 to 6. Right, that's where we start. And now we have the limit of the integral 0 to 3. So that's going to be 0 to b. And b is going to approach what? You need to be more specific than 3. 3 from the left. So 3 with a little minus on top. Yes, that's 3 from the left. Welcome to Calc 1 one-sided limits. Woo! So 3 from the left of dx over x minus 3. And then we're going to have a plus. And then there is a limit of a approaches 3 plus, because we are approaching from the right, of a to 6 of dx over x minus 3. What kind of integrals are these? Log. So limit b goes to 3 minus of ln of x minus 3 plus, separate problem, limit a goes to 3 plus of ln of x minus 3. Oh, computed, sorry, from 0 to b and computed from a to 0. This is equal to limit b goes to 3 minus of ln of b minus 3 minus ln of just 3, because you have 0 minus 3. 0 minus 3 is negative 3. Absolute value of negative 3 is positive 3, so that's what you have. The next one is plug in 0 first, so it's going to be plus ln of 3. Again, same, right? Plug in 0. 0 minus 3 is negative 3. Absolute value of negative 3 is positive 3. And then we have minus the limit of ln of a minus 3. So now my question to you is, what is this limit here, knowing that the graph of ln looks like this? What is the limit trying to approach on the x-axis? And what value y it produces? If you are to plug in b is 3, what do you get? And what's ln of 0? Shoots to negative infinity, right? Do we all see that? So inside this bubble, I have b minus 3. b minus 3, when I plug in b is 3. 3 minus 3 is 0. I'm getting ln of 0. ln of 0, which is right there, as the y value has negative infinity. So the first term is trying to hit negative infinity. These two guys will simply cancel. And then the third term will also try to hit negative infinity. Boom. You know what the scary part of this problem is? If you do this problem wrong, without this, you're going to get a number.
It's the A that part to positive.
No, it also approaches 3 from the right side. So you still have 3 minus 3 is 0, right? 3 minus 3 is 0, and So as I said, the scary part of this is that if you are to solve this problem wrong, you will get a number and you'll be happy with it until you try to build it and go, what happened? So you have to be very careful. Type 2 is evil.
So in what circumstance you're saying you get a number?
If you do it wrong.
Okay.
If you just do the problem, using your Calc 1 knowledge, right? If you are to give this to Calc 1 student is going to plow through. Because in Calc 1 you just, you just go and you compute, right? You don't have to think about much stuff. So, you get ln of x minus 3 from 0 to 6. And you plug in 6 minus 3 is 3, plug in 0, you get 3 still with the absolute value, right? So it works out. But it doesn't, as you can see, because it doesn't work out. It doesn't work out. So you have to be very careful. Let's take a look at more examples. I'm going to steal a couple of examples from the textbook, and well, actually, I don't need a textbook. Let's just have fun. Integral of x divided by the square root of x squared minus 4 dx from 0 to 2. They have a lot of wonderful examples. That was epic. I wish that was my soundtrack walking into any room. I know. What's going on? Oh yeah, I do have it backwards. You are right. Yeah, I do have this backwards. You are right. 4 minus x squared. You're right. Yeah, because it doesn't work the other way. We get complex values. Yeah? Oh, right. Would you like to hold it on the board?
I think stream dead.
Stream dead?
Yeah, so.
The bandwidth issues. It rained, so. Yeah. So do we have an issue in this problem?
Yes.
Yes, where's the issue? Vertical asymptote at 2. So that's the problem one. So that's the one that gets replaced with the limit. Great. So that's the first hurdle. Guys, does this look like an improper integral? Right? It doesn't until you examine it. You have to plug all of the numbers between 0 and 2 in your head and make sure that none of them make it, right? Great, so now that we took care of that, what integration technique am I going to use?
No, this. Is it in your sign? There's X.
It's asymptote.
There's X out.
Oh.
You can, but do you really need to use a sledgehammer or a little nail? Right? You can. So this is u sub because you have x squared and you have x for dx, so du, so u-hoo. Right, this problem is, you can use trig sub, sure. You can also come to class through Holland Tunnel. It's available to you unless they do, then pick a different tunnel. Given that you do not live in New York, right? You can stop by Washington, D.C. too. All right, so we start with the limit b goes to 2 from the left. And then we have 0 to b, and we have our x dx divided by the square root of 4 minus x squared. To integrate this, yes, you can use trig sub, but it's much easier to use u sub in this case. U equals 4 minus x squared, du equals negative 2x dx. I don't have a negative 2, so I'm going to fix that. Put negative 2 and negative half in front, and then we can deal with the problem. So I have negative 1/2 limit b goes to 2 minus, and then we have the integral. And now you have option of switching all of your limits to u, including the one in the limit, or leaving everything as is and then going back to x. So I have du over root u. And if you want to switch your limits, you would actually have to switch also b goes to 2. You'll have to switch that as well. Or actually, no, you don't, because you can plug in b. Now it becomes confusing, but the limits would be 4 and 4 minus b squared if you are switching limits. So now, negative 1/2 limit b goes to 2 minus from the left. And what's the integral? It's negative 2 square root of u. Right? Negative 2 square root of u, because u, this was u to the negative 1/2, plus 1 is positive 1/2, divided by 1/2, which gives us, oh, there's no negative. There's no negative, it's just positive. All right, cool. And that is computed from 4 to 4 minus b squared. Okay. We are dealing with this. Negative 1/2, limit b goes to 2 from the left. And then I have 2 times square root of 4 minus b squared minus 2 times square root of 4. Now, when b is equal to 2, b squared is 4. 4 minus 4 is 0. So this one goes to 0. And all I have is negative 1/2 times -4, which is 2. Cool, huh? Now this problem is from the textbook, so please don't. I send strongly worded email to them. X cubed divided by x to the 4th minus 1 dx.
Can you back up to the previous one for a minute? I just want to see what you did for the use of.
Oh, you sub?
Yeah. All right, got
There's
it.
a lot of lag. Oh, actually, wait, this one is easy. Aw. Yeah, I was aiming for partial fraction decomposition. I failed. Oh, I'm sorry. All right, so this is what? Limit, where's the problem?
1.
Problem is at 1, so we have b approaches 1 minus integral 0 to b x cubed over x to the 4th minus 1 dx u sub, so the same as the previous problem. You can solve that. Let's see. Well, I'll let you pick because you pick better problems. 39, 40, 41, 42. 39 through 42.
It's not on the board.
I know. 39 through 42.
41.
41. Oh. No, it's a different edition, so
Oh, okay.
Beginning to hate the letter E.
what do we do here? Do we have an issue in this problem? Is it a Calc 1 or Calc 2? Which one is the problem? 0 is the problem. Good. So limit a goes to 0 plus, because it's from the right, integral a to 1 of e to the root x divided by root x dx. Great. Which method do we use? Yeah, so boring, right? U equals root x, du equals, very good. Now I don't have this 2, so I'm going to fix that. Put the 2 in. And now I have 2 limit a goes to 0 plus, and the integral becomes e to the u du. Now plug these limits in the u substitution. We get root a, and we get 1, because square root of 1 is still 1. So now we don't have to go back to x. We can just finish all of this. So 2 limit a goes to 0 plus, integral of e to the u is e to the u, computed from root a to 1, which is 2 limit a goes to 0 plus, and I have u is 1, so e to the 1, which is just e minus e to the root a. Now how much is a? 0. So this is going to be what? E minus 1. Converges to 2e minus 1. It's about 3.4, right? I call it 3.5, whatever. About 3.5. Can we make this worse? Sure, right? Always can make it worse. Yes, we can make it impossible. Let's just do some theory crafting over here. Let's imagine the simplest partial fraction decomposition problem. Think about it a little bit, and then we're going to talk. So negative infinity to positive infinity dx over x plus 2 x minus 3. Lock the doors. So clearly integration is partial fraction decomposition, right? You have two linear terms, and this is the cheapest one, right? Because you have to have minimum 2 factors, and in this case they're both linear, so this would be a over x plus 2, and right? So no issues whatsoever, except issues. Can you tell me the issues?
-2 on this root.
Yes. We also see the infinities, right? So infinities are there for the display. But the real issues are the negative 2 and 3 vertical asymptotes that are there. If you are to go back to your partial fraction decomposition and find your partial fraction decomposition definite integral problems, you will see how carefully they pick the limits. So you do not end up with a vertical asymptote in any of the integrals. How many integrals do I need here? I have 2 students telling me that I need 4. This is where you start thinking, you start talking to the friends if you have any.
That's how my imagine.
You can phone home, right? The lifeline.
Phone.
Yeah. Who are you gonna call? Phone home, see.
So basically, it has two
Yeah,
axes. So you know you can't really just like
Right.
Sexist.
can't be two or
Oh, right. This- Bring it. Google.
So it's real.
How many integrals do I need? So far I have 3 and 4. 6. There we go. Yes.
Oh, wait.
Good job. 6 integrals. 6 integrals. Now, why is it 6 integrals? Well, think about it. We have 2 vertical asymptotes, and we have negative infinity and positive infinity. I need to approach this one. I need to approach that one. I need to approach this one. I need to approach that one. I need to approach that one. I need to approach that one. How many approaches do I have? I have 6 approaches. If I have 6 approaches, that's 6 integrals. So, what are those integrals? Well, these asymptotes are at negative 2 and 3. So I'm going to have integral from negative infinity to whatever number in between negative infinity and negative 2. So pick a value. Pick a value.
0.
How's 0 between negative infinity and negative 2?
Oh.
Negative 3 it is. Plus negative 3 to negative 2. And then here is your 0. From negative 2 to 0. And then from 0 to 3. And then from 3 to a value. Which one? 4. And then from 4 to positive infinity. Now when you look at these integrals, you have 6 integrals. Each one has exactly one bad point. Each one has exactly one bad point. You have a negative infinity, then you have a negative 2, then you have a negative 2, then you have a 3, then you have a 3, then positive infinity. Oh, that was the simplest? That was the simplest partial fraction embedded in the... Well, no, I mean, I put the infinity, right, infinities. That was cheap. That added extra integration, obviously. Easy, simple.
Getting
Yeah. You're getting excited over this. What are we going to do if the partial fraction decomposition has 4 terms? Right? Yeah. So what do we do for the test? We just do one partial fraction decomposition on the improper integral with 12 integrals, right? And that's it. I was kidding. So you have seen U sub, possible trig sub, partial fraction decomposition, and basic integrals embedded inside the improper integrals. Improper integrals are a way to compute integrals that are unbounded Unbounded meaning going to infinity, and the area under that integral can converge to a value, in which case we write that C converges to 1 or 1/2 or 1/3, whatever we had, or it can diverge if it goes to infinity. If I have multiple integrals like this, only one of them needs to go to infinity for the whole thing to blow up. All right? So if you have, like here, let's say, 6 integrals, 5 converge and 1 diverges, that's the only one that's going to ruin the party, right? You only need one to ruin it for all. So that's what we have. So make sure that, you know, if you have multiple integrals, and as long as one of them diverges, everything else immediately diverges.
You have a biparts. You do a biparts with this?
Of course, all of the techniques. So all of the techniques you learned, since there is a popular request over here, let's see if they have any by parts. And they do.
Not the evil ones.
They do have a problem by parts, yes.
So you're saying this one is not going to diverge, or it could?
This one?
Yeah.
This one is going to diverge.
Okay.
2 vertical asymptotes, so that's... you were saying something about by parts? I mean, we don't have to do it, but we could. It's a beautiful example. I don't know why they put the dy. You can change it into x's if you want to, but why is this by parts problem? Because you can't integrate, right? There is no y for u sub, right? There needs to be a y over here for u sub y squared. So it's not basic and it's not u sub. The only other option you have is going to be by parts, because it's not trig sub, and it's not partial fraction decomposition, because it's not division of polynomials. So literally by process of elimination, if you know all those 6, right, you eliminated basic and u sub immediately, you eliminated trig sub and partial fraction. The only one that stays is by parts. And now you have to just wrestle it on how to integrate by parts. But also my question now is, well, what's so bad about this problem? First of all, why is it? Because if I plug in 1 squared is 1, ln of 1 is 0, that's cool, and negative 1 squared is positive 1. So that there's no, yes? I here.
Not the ln of 0.
0, exactly. You have to split this into 2 integrals, negative 1 to 0, and then 0 to positive 1. And then you have to grind to this. Now, the cool thing is that both integrals will have the same integrand of ln y squared. So you are only doing by parts once, and then you will plug into both integrals. So that's a cool part. So we are going to split this first into negative 1 to 0, ln y squared dy, plus the integral 0 to 1 of ln y squared dy. And then we are going to put the limit of b goes to 0 minus, that's from the left, because minus 1 to 0, right? So by the way, guys, if you are confused with this from the left and from the right, if this is minus 1 and 0, and you are approaching 0, you are approaching from the left into an interval from minus 1 to 0, so that's why 0 minus. 0 minus means from the left. For the other one, it's going to be 0 to 1, and you are approaching right from the right. So imagine yourself walking over here, and you ask yourself, which direction am I coming from? You are coming from yeah. You are left of 0, you are coming from the left. You are walking right, but you are coming from the left. So x approaches from the left. That's the wording. Approaches from the left, so 0 minus. All right, so now we have the integral. I'll get rid of this now. There we go. 0 minus 1 to 0 ln y squared dy plus limit a approaches 0 plus, that's from the right, a to 1 ln y squared dy. Now we're supposed to integrate by parts because nothing else fits. We have u, dv, du, and v. Now, ln y squared, I can't integrate this in any way, so I'm going to just dump all of that here into u, and then dv will just have dy. When I integrate dy, I will get y, and when I differentiate this, I'm going to get, very good, 2 over y dy, yes. So now we're going to put our arrow that will help. And I'm just going to actually solve this part and then we can plug them into integrals. So I have y ln y squared minus the integral of y times 2 over y dy. These guys cancel. So the whole thing is y ln y squared minus 2y. So this is what is going to plug in for each of the integrals up there. So now we're switching back to black. Oh, come on. This computer is really getting slow. And
You just get it.
yeah, I know. Maybe it's like shoes. I have to kind of break it in. Yeah. Limit b goes to 0 minus, and now instead of the integral, I have this y ln y squared minus 2y computed from -1 to b, plus limit a goes to 0 plus of y ln y squared minus 2y from a to 1. So now all we need to do is to take the limits, right? And, oh, nice. Yes. Well, what did you do for this?
I put b in and b is 0, so ln of 0.
Yeah, what's ln of 0?
Infinity.
Negative infinity. And you have y in front, which is 0. So what do you have? 0 times. You have 0 times infinity, which is L'Hopital rule. Welcome to section 4.7 on Calculus 1. Let's go. Lock the doors. No one is leaving tonight. Class ends at 10 p.m. Please adjust your clocks. Let's go. We need to do L'Hopital rule for well, he wondered about the... Yeah, just to make sure that there is by parts. There it is. Just as a little bit extra added.
Stop there. How much partial credit would you get?
So limit of y ln y squared as y goes to 0. Now we need to solve this using L'Hopital rule. What do I have? I have 0 times infinity, which means we have to use the trick which you learned in Calc 1, which says f is equal to 1 over f to change it. So you're going to change the y, obviously. So this is going to be limit y goes to 0 of ln y squared divided by 1 over y. Now, by L'Hopital's rule, we take independent derivatives of numerator and denominator, because now we are at infinity over infinity, right? When you plug in 0, you get ln of 0, that's negative infinity. And when you divide 1 by 0, you also get infinity. So now when it's infinity over infinity, you can use L'Hopital's rule when you take independent derivatives. So you will have on the bottom negative 1 over y squared. That's the derivative of 1 over y. And on the top, you will have your 2 over y. So the whole thing simplifies into negative 2y. And when you send y equal to 0, we get 0. Beautiful. So, going back to our problem now, we have 0 plus negative 0 minus 2 times negative 1 plus, this is also going to be, now we plug in 1, so this is going to be ln of 1, which is 0, and then minus minus 2, thank you, and now we plug in a, so that will be minus 0, that is calculation from there, and then minus plus another 0. Okay, fine, there we go. So the whole thing is 0? Wow. Beautiful. You know what? This problem better be, this graph better be nicely symmetric. So what do we have? What was the problem? ln of y squared. ln, oh, I'm just going to put x squared. Look at that. Oh, by the way, this is an even function, so we could have just did half of the work if you double the integral from 0 to 1. It's an even function, but that's okay. Such is life. Well, I'll see you Wednesday. We'll talk differential equations, so you know what's up.
Can you back this thing? I just want to see.
So a little bit of L'Hopital. You know you're going to be writing it, right?
Yes.
And then we just meet next Wednesday.
You setting it for
Yeah, but you set it up for yourself.
Alright.
Yeah, I definitely didn't take double guess.
There goes the weekend, huh?
We can talk about it.
There goes the weekend. But that's okay. It gets much better. Next class, you'll be flying to stuff. Hi.
I thought the homework was going to be due this Wednesday.
Yeah, I have to open it now.
Oh no, before last class, because I wasn't here Monday, Wednesday, I was busy.
Yeah, the police is right here. I have to reopen all of the homework.
Okay, because it says it was due the 16th, the 17th,
Yeah.
and I was just like, oh.
Come on,
So,
let's see. I gotta sit here and do the homework.
Okay, and
Otherwise,
test 2.
Can you host the homework, please?
Yeah, and for test 2, what are the sections again? Just to double check that.
which chapter we're in? We're now chapter 8.
Yes.
So chapter 8.
Everything, all of them.
No, we're skipping the one that says other methods.
Other
I think that's 8.7. I think. I don't know. Whatever is called other methods.
So all chapters, all of the section in chapter 8 except
That one.
whatever that says other method and 9.1.
We did skip 8-7.
Alright.
9.7. Okay.
And then 9.1 and 9.3 from the differential
Okay.
equations.
Yeah. Okay. And the homework you're gonna fix it. And
Right
it's
now.
due Wednesday, correct?
I don't know. When is it due? When do you think it should be due?
Whenever you
December
want.
12th.
We did it in class.
December 12th. No one's gonna touch it, and then they're gonna get 12 on a test.
Because
Sounds like a them problem.
I was like, I was opening it today and it's like all past due. I'm like, hold on, wait, I just missed 2 classes. Like, that's it. You know,
About the movement on Thursday, about the leadership within the movement on Thursday, and then the next day, the exhibit opens in my hometown about the same stuff. So I said, wow, there was nothing happening. The last time I talked about the movement in a public setting was